We got like it's actually not this possible. It's by around it's not even on the fair, but that's two more impulses. Well, like Chris Davidson, like the bus, John sounded like theirs. Wow. But those are like those.
Okay, hello everyone. Congratulations on making it back from spring break, from our time change. Hopefully everybody's feeling good. I'm feeling a little dazed. I hope you're all a little better, but we'll make it through. If not. Okay, so where we're going to start off today is we're going to be working in the renal system. So I posted a link that I think was not previously available to you. So what we did before break was on your own, you viewed a video about the basic sort of anatomy of the renal system. So some of the parts that we're going to be talking about in this unit. And then we touched back on one of our final topics from our blood unit. So now we're going to jump back to the kidneys. As we come to our review for the exam, we'll go back to some of those blood topics and practice, but I want to make sure that we're well and deep into the kidneys so that we keep up with what's going on in the other classes and presumably what's going on a bit in lab. Okay, so we are going to be talking today about the first part of our nephron. So we're going to be starting up at the top with the beginning of our unit of the kidneys, our nephron. So just a reminder of where we are. So I know you all watched the video, but we're talking about our kidneys in our abdomen. They're roughly kidney bean shaped. They have a cortex, so an outer shell. Drawing this like a little bit of an ear here. And they have inner pyramids making up the medulla of the kidney. And we have different concentrations of ions and things in different parts of the kidneys. So we're going to be tracing our little units of the kidneys as they dive from the cortex down into the medulla, back out. And then the fluids that they're filtering out ultimately get dumped out of the kidney into the ureter and out your bladder. So that's fundamentally where we are when we're talking about the kidneys. Okay. So we're going to be talking about different parts up at the top of the nephron, which is what we'll be going through today. We have our glomerulus, which is a capillary bed. Okay. We have fluids that are going to get filtered out. So our first topic for today is going to be glomerular filtration. They're going to get caught by something called Bowman's capsule, which is made up of a space. Bowman's space looks kind of like a little Pac-Man eating this capillary bed. Okay. And then this capillary bed would go into a proximal convoluted tubule, proximal meaning nearer, just like when we talked about the proximal parts of limbs in anatomy. Then we'll have our nephron loop or loop of Henle diving down into the medulla, a distal convoluted tubule, and then we'll go into collecting ducts where our urine is stored. So that's the briefest of summaries of the parts of the kidney that we want to be able to remember as we start to talk about our processes. So hopefully we're all a little bit on the same page here. Okay. So we're talking about how we end up with urine, why we end up with urine, why we're filtering stuff at all, right? So fundamentally, that's what our kidneys are for. Our kidneys are for filtering your blood largely. So we're going to be regulating the ionic concentrations of your blood plasma by regulating what we take out of that plasma as it goes through the kidneys. So we can also, in this process, regulate how much blood plasma you have, and therefore literally the volume of your blood volume, which would lead into like blood pressure, by figuring out how much water should we take out of the plasma and excrete out as urine. Okay, so those are some of the big major things that your kidneys are doing for you every day. So along the way, they're regulating osmolarity of the plasma, they're regulating pH of the plasma. It's going to affect all your other organ systems as well, right? Because what's in the plasma, what you have dissolved in that plasma. The pH of that plasma makes a difference for the environment the tissues of your other organs are interacting with. We're also going to be removing metabolic waste products as we are filtering things out of the plasma at the kidneys. We've also mentioned the kidneys a time or so before. Chiefly, we mentioned them when we were talking about the production of red blood cells, or erythrocytes. So we mentioned them because they do produce some hormones. So one of them is erythropoietin, which was that signal to your bone marrow telling you to make more blood cells, right? So part of why that makes sense kind of on a more global whole body level, right? It's because the plasma, your blood, is coming through the kidneys, it's being filtered. So the kidneys kind of see what's in the blood as they're figuring out, what do we take out, what do we leave in, right? So it's a good place to have a signal for, okay, we need more red blood cells coming from the kidneys. So other functions of the kidneys, in addition to this filtering process that we're really going to focus on, is the secretion of erythropoietin and another hormone, renin. They also help activate some vitamins, particularly vitamin D3. And they can make new glucose. So way back to our metabolism unit in the fall, the kidneys are able to do gluconeogenesis, so they can make new glucose from other products. The main thing we think about when we think about kidneys is filtration. Okay, so words we're going to use for processes in this unit, we're going to be thinking about filtration, we're going to be thinking about reabsorption, we're going to be thinking about secretion, and we're going to be thinking about excretion. So filtration and reabsorption are going to work pretty much the same as when we talked about net filtration pressure and capillaries back when we were talking in our cardiovascular unit about what's happening near our tissue, how do we have things going back and forth between the tissue. So our first step of this process that we're thinking of, our glomerular filtration up at the top of our nephron, okay, is going to work that same way. It's just specialized. We're going to have some specialized terms because we're now focusing specifically on the glomerulus, which is a modified capillary bed, and the nephron and the kidney and all their very specific features, as opposed to thinking about just a general capillary bed. But anything that helped you understand net filtration pressures back when we were talking about capillaries, try to apply that here to this sort of variation on it. Okay, so when we're thinking about the glomerulus, we have arterioles coming into it. So we have our afferent meaning going to arteriole. Our efferent arteriole is going to be coming out of it. Okay. And then the glomerulus itself is a bunch of swirling capillaries between the two. Okay. So that's our glomerulus. So we have blood traveling into the glomerulus, around and through the capillary bed, and then out this efferent arteriole. Okay. So in this process, we are going to end up taking out 125 milliliters per minute of that plasma and pushing it into the nephrons of the kidney. Okay. So our filtration, we're filtering an awful lot of fluid. So remember, filtration before, just like now, is when we take fluid from inside the blood vessel, so in this case, the glomerulus, inside the capillary, and move it out of the blood into some new space, right? So when we say we're filtering from the glomerulus to Bowman's capsule, we mean we have fluid moving from inside those capillaries into our nephron. So 125 milliliters per minute, or 180 liters a day, is ending up flowing through those kidneys. That's an awful lot more fluid than you have blood. So you sit and think about this for a second. It should hopefully be obvious that you're not going to pee out all of that fluid, right? We're going to make adjustments as we go through the nephrons because you do not have 180 liters of fluid in your body to just pee out if we went straight to the ureters and straight to the bladder. So we're going to have this fluid traveling into the nephrons, this functional unit of the kidney, but then we're also going to be taking stuff back out of that fluid and moving it back into the blood, back into the body, which is why we now are going to be using the word reabsorption instead of absorption, like when we talked about net filtration pressures before. So when we talk about reabsorption, we're going to be talking about stuff that has been filtered out of the glomerular capillaries. So it's in the nephron, then we move it back to the blood because we want to keep it in our body because we want to keep a bunch of that fluid. Okay. Right. So 125 milliliters per minute or 100 liters a day of protein-free plasma are moving into Bloemann's capsule. So pretty much everything other than the proteins in your blood is moving into the nephron to get filtered, to get basically reevaluated, reassessed, right? We're readjusting concentrations of all sorts of things. We're just not moving proteins, they're big, okay? So in order to get into the nephron, that filtrate, so the filtrate is that fluid that's eventually going to become urine after we make all our adjustments to its concentrations. So that's that 125 milliliters per minute, that glomerular filtrate. It's crossing a couple barriers, okay? So we're starting out with that fluid in the capillary of the glomerulus, okay? This is a fenestrated capillary, so it's pretty loose. It has like gaps, basically. So it's got kind of windows in it. Okay. So we're going to go through the fenestrated capillaries. So we can see these kind of pores, these holes in the wall of the capillary itself. So the capillary endothelium is that lining of the capillary. So that would be a cell layer. Okay. The filtrate then has to cross a basement membrane. So that's this middle layer here. Okay. And then it's going to go through these features called filtration slits. So we have another layer of cells sitting on top of this capillary bed. So this is part of our glomerular capsule. And these cells are called podocytes. Whenever you see like pod or ped, these are roots that kind of mean feet. So what these are cells with these sort of foot processes that partially cover over the outer layer of this capillary, but leave these slit pores that are pretty big, which is why we can have almost everything except proteins crossing over. Okay. So we got to go through the capillary endothelium, the basement membrane, and then we cross through these filtration slits among the podocyte foot processes. Okay. So that takes us from inside this capillary, the glomerulus, and into this space, which is Bowman's space. Okay. If we refer to Bowman's space or Bowman's capsule, those are pretty similar terms. So I'm just going to point out. So space, I'm just referring to like anything you would highlight in the gap here. The capsule would just be the capsule kind of grabbing it. Okay. So those are pretty interchangeable. The only difference there is kind of what we're emphasizing when we use those two different terms. Okay. So we have forces that affect how much plasma we're filtering, how much filtrate ends up in the nephron. Okay. So these forces are going to be really similar to when we were talking about our net filtration pressures, right? So ultimately, to figure out what our pressures for glomerular filtration are, we're going to be adding up forces that favor filtration, right? So forces that either push fluid into the nephron or pull it into the nephron, right? So we can have a push or we can have a pull, but filtration is always this direction into the nephron, into Bowman's capsule. So we'll end up adding together these forces for filtration, okay? And then we're going to subtract out any forces that oppose that. So anything that keeps fluid in the capillary. So any pulls or pushes towards our glomerular capillary are going to oppose this, okay? So our equation looks kind of similar to when we're talking about net filtration pressure, just now we're specifying glomerular capillary or Bowman's capsule, whereas before we were talking about either just our capillary or our interstitial fluid, right? So we're just specifying new locations, but the idea is the same thing. So we're going to add together any forces that's forcing fluid into the nephron. We're subtracting out any forces that keep fluid in the capillary, and we're going to get an overall glomerular filtration pressure when we do this. Okay. The symbols for these different pieces of our equation also mirror what we saw when we talked about net filtration pressure. So we are again going to have hydrostatic pressures. So hydrostatic pressures are a big P. Okay. So remember, a hydrostatic pressure, hydro meaning water, static means position or something. So a hydrostatic pressure is when you have some fluid and it's pushing on the walls of its container, right? So hydrostatic pressure is a pressure because you're pushing on the walls with that fluid, pushing out, okay? So we can see that in our first example here of a Starling force for our glomerular filtration pressure. That's the name for these different forces. So our Starling forces, this first one, the glomerular capillary hydrostatic pressure, which is symbolized with a big P, and then GC for glomerular capillary. Okay. It's telling us that the pressure of that plasma, that fluid in the capillary, pushes out on the walls of the capillary. So we're saying we have fluid, and here we'll have a droplet right here in our capillary. It's pushing against the wall, pushing out towards the rest of the nephron. So that's why this favors filtration. Okay. So our other type of Starling force, it's also another type of force we saw. Okay. So before, we talked about our oncotic pressures as well. Okay. So an oncotic pressure, oncotic is referring to proteins, which are impermeable solutes, meaning things that can't cross the wall, right? Okay. So when we have a situation, just in general in a cell, right, or any system, if we have a solute that can't move, right? So if this little X solute could move to reach equilibrium, it would just move away from where it's all grouped together so that we could evenly space things out, right? That's our equilibrium state, everything just evenly spaced. But if we have a solute that can't cross some membrane, the other way we can get even spacing is to have water move towards where it is and just kind of push them out, space them out farther away from each other, right? That's our process of osmosis, right? That's why it happens when we have impermeable solutes. So we have water move instead. Okay. So that's the kind of process we're thinking about when we think about our oncotic pressures. Okay, so oncotic pressures are notated with our little pi symbol. This is telling us that we're thinking about the oncotic pressure of Bowman's capsule. So what we're saying is any proteins that we have in this space, right, would draw water towards them in order to space them out to try and reach equilibrium. So they would pull fluid towards them because that fluid, that water, would want to space them out farther. Okay. So this direction, this pull, is also leading us towards the nephron, into the nephron. So this is also a pressure for filtration. Okay. Right. So pausing here because these first two are our pressures for filtration. So they're the first part of this equation. Okay. What you're going to note is that we have a pretty high pressure when we're thinking about the glomerular capillary hydrostatic pressure. It's actually higher than our hydrostatic pressures when we're thinking about net filtration pressure in our normal capillaries. That's because our afferent arteriole is pretty wide. So it has a high radius, high diameter, low resistance. Then we go through this curvy capillary, and our efferent arteriole going away is narrower. So it has a low radius, high resistance. So we basically get blood and pressure kind of backing up in the glomerular capillary, which is great because we actually do want to filter a bunch. So we have a high hydrostatic capillary pressure in the glomerulus. And since what's crossing is protein-free plasma into Bowman's capsule because of those layers of the capsule itself, while we theoretically have a Starling force for Bowman's capsule oncotic pressure, under normal conditions, proteins shouldn't be crossing, so there shouldn't be any proteins in that space. So we leave it on here for completion because in disease states, things always get weird, but it's 0 under normal conditions because all the proteins should be staying in your glomerular capillary because of our layers. So before we walk through these next two forces, our forces imposing filtration, questions about either the overall hydrostatic pressure, oncotic pressure concept, because I know we did it before, but it's been a little while, or about these two forces for filtration, or the idea of what filtration means for our kidney.
If it's positive, is that filtration? If it's negative, is it filtration?
Yep. Yeah, so that's why we start with our filtration pressures, right? Because if our filtration pressures are bigger, you'll get a positive number, which will mean you'll have filtration. And when we're thinking about our kidneys, I think you pretty much really always will have some filtration happening. We'll just be thinking about differences in rates now, rather than which direction. Your kidneys, I can't think of conditions in which your kidneys are giving stuff back to the glomerulus anyway. Any other questions at this point? Okay, so our other two forces are anything that pulls fluid back towards the glomerulus. So anything taking us back in this direction. This is why I always like to draw it out for myself. Seeing is believing, drawing is believing, at least for me. Okay, so anything going back towards our capillary bed is going to be a force opposing filtration. So it's going to be a force that we have to subtract out in this equation. Okay, so we are again going to have a hydrostatic pressure, so a big P, and an oncotic pressure, a little pi. Okay. They're just going to be the reverse of the ones that we just talked about, but we can think them through too, instead of just remembering, right? So when we're thinking about a hydrostatic pressure that opposes filtration, we know that a hydrostatic pressure is something pushing against the walls of its container because there's a fluid, right? That means we're thinking about fluid droplets already in this space, essentially, pushing against this wall, right? So that's going to be our hydrostatic pressure pushing back, okay? So we would describe that as the hydrostatic pressure, big P, of the fluid in Bowman's capsule, which is why that's PVC, our Bowman's capsule hydrostatic pressure. So as fluid sort of swells into the space, it pushes back a little bit towards the capillary bed. So for an oncotic pressure, our oncotic pressure, we can sometimes think of like as a pull, right, on water, right? Because it's the pull of a bunch of proteins that can't move across a membrane. So they're pulling water towards them instead, right, in order to space out and reach equilibrium. Okay. So when we think about our pull, we're going to be thinking about proteins still in the plasma, okay, of which there will actually be many, right, because we're removing all the plasma, all that protein-free plasma, and we're essentially like concentrating down those proteins, leaving them in the glomerulus, okay, and they're pulling fluid back towards them because they don't want to be all jammed up close together. They want to space out. Okay, so these proteins pulling water towards them, we drew our little X's in the glomerular capillary. So this is the oncotic pressure of the glomerular capillary. So those are our two forces opposing filtration. So they're the ones we subtract out here in this equation. Okay. And for these, we will expect there to be a value for each of them. Okay. So there is fluid in Bowman's capsule. So we do have a hydrostatic pressure in the capsule. There shouldn't be proteins there. So its oncotic pressure was hopefully 0, but there is fluid. That's the whole point of the kidneys, is that we did take fluid out. Okay, so under typical conditions, it's about 15. Okay. And we do also have lots of proteins that we're leaving in the glomerulus, right? We're filtering everything out except for those proteins. Okay, so we're gonna start out here with 29 millimeters of mercury as our measurement for that oncotic pressure of the proteins that are in the blood in the capillary. Okay, so we subtract those two numbers added together from our overall forces for filtration, and that gives us our overall glomerular filtration pressure. Okay, so when we talk about glomerular filtration, do note we're going to have a lot of similar seeming terms, so it's worth noting now that this is going to be our filtration pressure. We're also going to be thinking about a filtration rate. I think we have a filtration fraction. Okay, so I'm just going to point out these were all pressures for filtration or against filtration. They're measured in a pressure unit, millimeters of mercury, right? So we have a pressure number at the end here. Okay, so if I give you something in like milliliters per minute, that's not a pressure, right? That's going to be some type of a rate because it has time in it. You have a pressure, this is a pressure measurement. So that's how we figure out our glomerular filtration pressure, and changing these things could change our overall pressure for filtration. So here we have this written out in terms. Okay, so our Starling forces favoring filtration in words are our glomerular capillary hydrostatic pressure, 60 millimeters of mercury. It's pretty high because that efferent arterial, efferent meaning something that's leaving, going away. It's pretty narrow, high resistance. So you can basically think it's pressure building up in the glomerular capillary, which happens before you get to that efferent arterial, right? It's got like a narrow little off ramp off this highway. Traffic is backing up. Okay. The oncotic pressure in Bowman's capsule, pulling fluid towards it, pretty much theoretical under normal conditions because there should not be protein in the filtrate. But if we have some type of disease that's injuring or damaging our kidney, there might be protein in the filtrate. Okay, so we don't want to not know which direction it will go. Okay, so the Starling forces opposing the filtration, both do have numbers attached to them. So the Bowman's capsule hydrostatic pressure is from fluid in Bowman's capsule pushing back towards those capillaries. It's pretty high compared to our other capillaries that we talked about generally in your system. Okay, this is because we are filtering out a lot of filtrate pretty quick, and that Bowman's capsule is not very big, right? It's at 100 liters per day of filtrate is going through here, right? So that builds up a bit. Okay. Then the glomerular oncotic pressure is high, 29 millimeters of mercury, because we have lots of plasma proteins in that plasma, and we are constantly moving fluid out, moving filtrate into the nephron, leaving those proteins back in that smaller volume of plasma continuing on. Okay. So here this is just drawn out big for you if you want to practice. Okay. So just a note, this was in our anatomy stuff. So when we talk about all of this together, the glomerulus, Bowman's capsule, Bowman's space, we'll also refer to this as the renal corpuscle. Spelling that is difficult. I always say corpuscle, so I assume I say that because that's how it's spelled. Okay, so these things together, when you see that, is just referring to this beginning of our nephron, essentially. Okay. Cool. All right, so those were our pressures. Now we're going to think about a rate, okay? So we know now the forces that are creating filtration. So the forces that are forcing fluid into the nephron, into the kidney. Now we want to think about how much fluid, how fast, okay? And this is something that can vary, okay, and will vary. So when we're thinking about our glomerular filtration rate, sorry, okay, we're going to have something measured in milliliters per minute, okay? Milliliters per minute, so a volume per minute, a rate, like a speed, okay? So what we're looking at here is that for your renal plasma flow, what that means, it's like how much blood is going to your kidney overall. Because we're not going to completely suck dry all your blood as it passes through a single nephron, right? We are going to leave some fluid in there, right? Otherwise, you can think of just like chunky sandy proteins kind of stuck in there. That wouldn't work. So our renal plasma flow, the blood going to the kidney, is about 625 milliliters per minute. These are typical numbers, okay? So 625 milliliters per minute come in and start doing their thing, flowing around, okay? And plenty of that blood, that plasma, is going to continue on in the cardiovascular system. It's going to go from our efferent arterioles actually to another series of capillaries that are lying along the nephron called our peritubular capillaries, okay? So we'll talk about them later, okay? But we do see that the amount of plasma coming in versus the amount of plasma leaving is not the same, okay? So the glomerular filtration rate is just the difference here. So we are losing 125 milliliters per minute of fluid that went into our nephron and then didn't come out, at least through the efferent arteriole, okay? So that is what we've shuffled into the nephron. So we have filtered 125 milliliters per minute into the nephron. So 125 milliliters of that plasma is on its way to potentially become urine. Exactly how much we excrete is going to depend on a lot of factors that we'll talk about throughout this unit. But starting right at the top, our typical glomerular filtration rate is 125 milliliters per minute. Okay. Okay. So this, you can see, is much higher than the filtration that we saw in our systemic capillaries. So in our systemic capillaries, when we were talking about net filtration pressure, our overall net filtration pressure when we added it up was often something like 2 overall, okay? And we had a filtration rate of about 3 liters per day, okay? We now have a typical filtration pressure of, we just calculated out like 16, right? Now we have a much, much higher filtration rate than we did before. So this is how we get that 180 liters per day. So these are just our typical values here. Okay. So the next thing we're looking at is a filtration fraction. Okay. So when we talk about the filtration fraction, what we're doing is we're comparing, okay, how much filtrate went into the nephron, into the kidney, versus how much plasma got to the kidney in the first place, okay? So this is actually pretty good because it means we can give relative rates, right? You can imagine things that change your plasma flow to the kidney. You can imagine things that change the filtration rate. So we can now compare those two directly instead of using these kind of absolute numbers. So for our filtration fraction, we're going to take that glomerular filtration rate. That's what GFR is. So you'll see this word a lot because we're going to have like feedback loops and stuff involving GFR. Okay. So glomerular filtration rate, that was the 125. Okay. So 125 milliliters per minute on top, divided by the total amount of plasma that was coming to the kidney per minute, which was 625. Okay. So we can see that that gives us about a 20% filtration fraction, dividing those two numbers. Okay, so about 20% of the plasma that was in the blood in this situation, in this typical normal example, got filtered into the nephrons per minute. Okay. Per minute, 125 milliliters out of 625, 20% of the plasma is getting cleared, prepared, adjusted, all the processes that we're going to see our nephrons doing. All right. So our next concept is filtered load. Okay. So when we're thinking about filtered load, we're now thinking about things that are dissolved in that plasma that are getting filtered. Okay. So for our filtered load, what we would do for this is that we are going to be calculating our filtration rate, GFR. So that's 125 milliliters per minute. And then we can just multiply that by the amount of whatever molecule we're tracking, its concentration essentially in the plasma. Okay. So the quantity filtered of that molecule is our filtered load essentially. So it depends on the glomerular filtration rate. Okay, so typical is 125, but if you're suddenly filtering whatever, like 300 milliliters per minute of plasma, then you would have a larger filtered load as well. Okay. It's also going to depend on the concentration of whatever molecule you're tracking. Okay. Usually we're often talking about glucose because glucose is really important for people's lives, and really important when we think about the kidney, and we'll see why. It's one of the main things that we're going to see filtering and then being reabsorbed at the top of the nephron, essentially. Okay. So we're going to be multiplying whatever our rate is by the plasma concentration of our solute. Okay. So we do like to track glucose for a bunch of this stuff. Like one of the tests for diabetes, right, is like, are you peeing out glucose a little bit? Apparently in the olden days, they used to like taste people's urine a little bit to see if it tasted sweet, to see whether they were appropriately filtering glucose. Okay. Crazy, right? But that's one of the reasons that we track glucose as we're thinking about the kidneys, right? Is this is an observable potential problem. Okay, so for our normal situation with glucose, we're going to start with our normal glomerular filtration rate of 125 milliliters per minute. Okay, our normal amount of plasma glucose is 100 milligrams per deciliter, which comes out to 1 milligram per milliliter. We're just converting units here. Okay, so we would then multiply that across, okay, to see how much glucose is ending up in our nephron, essentially. Okay, so we have 125 milliliters per minute. Very conveniently, we end up with 1 milligram of glucose per milliliter here. So our filtered load for glucose is 125 milligrams of glucose per minute going into that filtrate in the kidneys. So recap, our filtration pressures are what are the forces for fluid to enter our nephron to actually get filtered through the kidney. So that's going to be a pressure, okay, the glomerular filtration pressure. Then we have our glomerular filtration rate, which is telling us how many milliliters of plasma are ending up in the nephron, because it's not all of your plasma, but it is an awful lot. Our filtration fraction, it's just a fraction or a percent of the total blood flow, the total plasma flow to the kidney, to the nephron. So under this normal condition, it's about 20% of your plasma is ending up filtered into our kidney. And then when we think about filtered load, you want to think about your plasma as being like loaded up with solutes, it's loaded up with glucose, it's loaded up with all sorts of things. Okay, so our filtered load, you're thinking about the concentration of some solute in that plasma and how much of it, therefore, is ending up here filtered into our nephron. Okay, so these are a lot of similar ideas, but different things we can measure and different things we would want to measure depending on what exactly we're trying to assess. Okay. So we do regulate our filtration rate. So we have 180 liters of fluid that are getting filtered every day. but you are not peeing out 180 liters per day. I don't know if you could drink that fast if you wanted to, right? You're only going to excrete about 100 or about 1.5 liters of urine per day. So that's less than 1% of this fluid that was getting filtered. So this means that almost all that fluid that we take from the glomerular capillaries becomes filtrate in the nephron. 99% of it or more is going to get reabsorbed back into your bloodstream, only leaving a little bit to exit your body as urine. Okay. However, that glomerular filtration rate, notice it was 125 milliliters per minute, right? Per minute. So any small change in that really adds up, right? If you have a small increase in that glomerular filtration rate, adds up minute by minute by minute. So it's going to end up in a really large increase in the fluid filtered, okay? And ultimately, your body can only reabsorb fluid so fast. So it will also potentially really add up when we think about how much fluid is getting excreted, okay? So we do have strong regulation of that glomerular filtration rate, right? Because we don't want you to excrete way too much fluid, because that fluid is your plasma, right? You do not want to drop your plasma volume down too low, because then you're dropping your blood volume too low. And you don't have enough blood in your body circulating around, right? It affects your blood pressure, affects how much blood is going to be getting to all your organs, right? So we really have to regulate that glomerular filtration rate pretty tightly, okay? So this is highly regulated, and soon be time to come back to it. But the example at the beginning of class on like syllabus day, we watched that guy talk about his issues of falling and stuff, his Parkinson's and his issues with orthostatic hypotension, some type of hypotension, right? We talked about some of the ways that they could fix that, and one of them had to do with salt, right? That's because of this relationship of salt and kidneys and blood volume that we're going to be talking about in this unit. Okay. So when we think about our regulation of that glomerular filtration rate, so what we see happening here is our mean arterial pressure. Okay. So this is our pressure in the arteries, right? So our pressure in the arteries leads to pressure downstream, right? Pressure in our arterioles, therefore pressure in the capillaries, like pressure in the glomerular capillaries, right? So this pressure is essentially going to be affecting one of those main drivers for filtration, that glomerular capillary hydrostatic pressure, right? If you have a higher blood pressure, you have a higher sort of fluid push on the walls of that capillary, right? So without regulation mechanisms, you would end up filtering a lot more fluid, okay? So we can see that outside of a certain range, we do have a strong effect of arterial pressure on what we're looking at on our y-axis, which is our GFR, our glomerular filtration rate, which we typically see at 125 milliliters per minute. Okay, so 125 is this plateau here, right? So you can see that here between a mean arterial pressure of 80 and 180, there's not much variation at all there on the glomerular filtration rate, right? That is because of this tight regulation, okay? But if we overcome our regulatory mechanisms, you can see that outside of this zone, any tiny little change in mean arterial pressure where our mechanisms for controlling it don't work really shoot up our glomerular filtration rate. And you can see if we have a really low mean arterial pressure, way down low, right? That is also somewhat difficult to control, right? Because we just don't have high enough pressure yet. So we can see that if we have a really low blood pressure, we'll have a lower glomerular filtration rate. But we have this big plateau zone in the center. Cool. So some of the mechanisms here have to do with structures next to the renal corpuscle. So here we're just looking at a different picture. So here we see our afferent arteriole coming in. This is our swirly glomerulus here. So that's all those capillaries. These little donut things are our red blood cells. Okay. They're not getting into the filtrate either. Okay. So they're staying in our plasma. Here's our afferent glomerular arteriole leaving. Okay. So surrounding here, we see Bowman's capsule. Okay. Got Bowman's capsule. Starting off our nephron, eventually continuing into our tubules over that way. Okay. But our tubules do all kind of swirl back around at the end, the total shape of the nephron. You can see here. All right, we have our glomerulus and this blood flow at the beginning. We go through a bunch of twists and turns, but at the end, we skim by these arterioles again before we send our filtrate out as urine. Okay, so we have some structures here in this juxtaglomerular complex. We have macula densa cells. We have extraglomerular mesangial cells. We have granular cells all kind of touching here together. So macula densa cells, extraglomerular cells, granular cells. Okay, so some of these are going to be involved in how we are regulating that glomerular filtration. Okay. So our first way of regulating that glomerular filtration is just through myogenic regulation. So myo meaning muscle. So myogenic like genesis, so generated by the muscles. So our arterioles are still just arterioles. They have smooth muscle in them. They can contract. So essentially, if they get stretched out, they want to bounce back. That's a thing that we've seen in smooth muscle before, right? Like when we talked about vascular spasms as well, right? That was a kind of concept we thought about. So one of the ways that we can regulate that GFR is through myogenic regulation. So that bouncing back of the arterioles, you get too much blood flow, it's swelling, the smooth muscle is going to bounce back, kind of cut that down a little bit, lead to a little less blood flow flooding into the kidneys. We also have tubuloglomerular feedback. Right? In tubuloglomerular feedback, our macula densa cells are going to be secreting out paracrine factors. So that's like a local signal, essentially. So these cells, the macular densa cells, that are basically part of the end of the nephron, right? They sense fluid and the concentrations of things in those fluid coming back up and about to become urine. They can send out a signal, say, hey, this is too much fluid, this is not enough fluid, right? Because they're touching these arterioles at the beginning, they can partially change their radius and therefore their resistance, therefore how much fluid is getting into the glomerulus as well. Okay, so in tubuloglomerular feedback, the smooth muscle of the arterioles is responding to the signaling of those macula densa cells. There's also a third thing called mesangial cell contraction. So mesangial cells are here nested kind of between the capillaries. So theoretically, they can also kind of contract to kind of slow down this flow as well if we are getting a glomerular filtration rate that is getting too high, right? Because we really want to keep it here in this plateau of 125. Good. So I'll leave you there for today.